So welcome to 6th quad day at LSU. Today my presentation is about design of microresonators to minimize thermal noise below the standard quantum limit. This is the work I collaborate with LIGO group and Dr. Thomas Corby, which I really honored to. So after the famous Albert Einstein paper in 1915, the LIGO gravitational wave detector in Livingston and Hanford had their first detection in 2015, which was open a big door to this area. So here I show a very basic microson interferometer with resonance arc cavity. So after the continuous wave beam come from the laser, it hit the beam splitter, it go through the arm and hit the mirror, back to the beam splitter and detect in photodetector. So if in this go back and forth, any wave comes, or any gravitational wave comes, imagine this green circle is look like Earth. So that wave leads to the Earth from one side scratch and from other side screw, which lead to change the phase of the beam inside of the arms, which we measure it with this delta L, and that change of the phase, we can detect it here at beam splitter. They come together in beam splitter, and we can measure them in photodetector, in here with our photodetector. I don't know why this error comes. Okay. So from 2015, the direct detection of gravitational wave from binary system has been a huge success, already resulting in a Nobel Prize. And from 2019, the LIGO run 3 main tests, O1, O2, and O3, which lead to almost 50 detect of different gravitational waves. But we are still hungry and we want to do the system better, even if we are right now very good in filtering a lot of noises. So here I just introduce some common noises, which you can see like seismic noises, thermal noises, and quantum noises, and the effect of each of them, how they affect. So here I show you the advanced LIGO design sensitivity noise budget. So if you look at this red thick graph, it's look at this black graph come from total noise. It is total noise. It mostly come from quantum noise in most of the frequency. So this quantum noise, we can divide it into two kind of noise, which is shot noise and quantum radiation pressure noise. So shot noise come from the nature of the light. When we detect the light, we have some error to counting the photon, which we name it shot noise. And we can make the shot noise better by increase the power. And quantum radiation pressure noise is when the light back from the mirror, it carries some momentum, which that momentum we name them quantum radiation pressure noise. So far, shot noise, so far we could reach the shot noise and get all the noise down enough to see the shot noise. But quantum radiation pressure noise is very, very weak. So we couldn't reach the quantum radiation pressure noise yet. So our goal is to decrease other noise as much as help us to see the quantum radiation pressure noise, because we expecting that in future LIGO, this noise will stop us. what is the solution? There are several different solutions to catch the quantum radiation pressure noise. One of them is, okay, let's design a new microresonator, which I work on this project. The other one is, okay, don't use like a regular light, go to squeeze light, or get like, go to, use like non-linear crystal, or no, go to quantum motivated squeeze light. So if you want to use quantum motivated squeeze light, you have to deal with the very noisy feedback, which we need to make this squeeze light, which I work on this project too, but it's not here. I'm not going to present it here. If you like, I can present it in next call. And there's also other solution like quantum back action evasion, which means like instead of using the reflected light, we are coming to use transfer light. Which here I'm not going to talk about this either, but I just mentioned that, okay, there is more than one solution. So here I show, here you can see the LIGO design, the mirror that they already use it in real LIGO detector in Livingstone or Hansford. The structure here is basically is based on silica tantalum doped tantalum, and this mirror has a very high dielectric contract, very low optical absorption, and low thermal noise. But recently, Dr. Corbett students' paper in Nature offer a new design based on gallium arsenide, aluminum gallium arsenide, which gallium arsenide is very high reflective index material, and aluminum gallium arsenide is very low index reflective index material, which make a very good pair together. And they offer this design, which is great promise for reduced Browning coating thermal noise. So, but this design has one gap on it. On this design, they first designed the mirror separately, which is the 22 pair of gallium arsenide, aluminum gallium arsenide. They designed the mirror separately, and they connect these two together. So based on that, the mirror thickness is too much. It's like 4.75 micrometer. So when the thickness is too much, signal to noise ratio will decrease. What I did, I tried to decrease this thickness to increase the ratio of signal to the signal to noise ratio. So here you can see that here is the mirror we already made in the lab based on this design with different cantilever and different radius and so on. We use it right now in the lab and we test it. Here is the setup, and here is the place of the mirror. I bring the mirror speak here to show you that which part I study. First, I use the genetic algorithm to reduce this TH, which is the thickness of the mirror. And after that, I use the console to run finite element method to study over the radius and different geometry in cantilever, and also the place of the laser will hit the mirror. So here, this design is a reference design, which I showed you before. And first, what I did, I said, okay, let's kick the cantilever out and just transfer one layer of mirror below the indium gallium phosphide and see does we still have the 100% reflection, because here for us is very, very important that our mirror has like 99.999% reflection, almost 100%. We have never could catch 100%, but we are catching 99.999% reflection. So for this design, I said, okay, that's perfect. We reduce almost 355 nanometer easily, and we use one pair of mirror instead of cantilever, and that we have seen a microresonator. But after that, I run it over the genetic algorithm, and I try to find something better, and I reduce this part of cantilever like this, but this one wasn't successful either. This one was not bad, but we looked for something better, but this one wasn't successful because this part was very fragile and it couldn't tolerate the heaviness of the mirror. I'm just again show here that what I'm talking about. This part after red is this cantilever. That doesn't show well. And this part is the mirror on top. So we put the minimum of 50 nanometer, fix it on 50 nanometer to do not let it go below 50 nanometer, and we found three structure, which here Tg gallium arsenide, T aluminum gallium arsenide, the number shows here. And you might here ask me, okay, why I keep this 22 pair fixed? Why I didn't change this? The answer is I did change this, and I tried to find also a mirror. We even different different thickness to get like 100% reflection, 99.999% reflection, but I never could find something to be thinner than this. That's why we are stuck in this structure. And we just play with the one we shifted over after indium gallium phosphide, and we use it as a cantilever as well. Yeah.
But when you say you tried something, what do you mean? You didn't physically build it? Did
No.
You,
as I mentioned, I wrote a code based on genetic algorithm.
Okay.
And I modeled this on my code, and after that I defined that, okay, what material I want to be, and after that I let the genetic algorithm to run to find the thickness based on the reflection I want.
Okay.
Sorry about that. It's the gift I got after my graduation. So, yeah, we haven't built this structure because it takes 1 year to physically make it.
On the previous slide, it looked like maybe you built about 20 of them. Did I interpret that correctly?
Yeah, the previous
Or maybe 2 slides ago.
Sure.
Yeah, that's
One?
right. It looks like you built a whole bunch of them.
Yeah.
Okay.
The point is, it will be clear for you why we make
Okay.
a bunch of them.
Okay.
Okay. Now here you can see the result of this graph is the thermal noise. This graph is a standard quantum limit. So the black graph is our reference, which is the published paper in Nature. The red and blue is 2 of my design. Based on other parameter, I change in the microresonator based on the cantilever length, thickness, radius, and so on. So you can see, like for example, in the black one, we want that this fundamental mode be between 100 Hz and 1K. If it is below 100K, the structure will be very fragile. If it is above 1K, 100 Hz, 1K. If it's above 1K, the thermal noise is a lot. So you can see, like, for example, this black graph is very close to 1K, but for me is shift that way, which is more safe. It means we have low thermal noise, but we still have enough distance of the 100 hertz, which is the boundary of being fragile, having fragile microresonator. And also, if you see the black graph, it has several modes, like 1, 2, 3, 4, 5, and 5 is look like it's exactly at the middle of what I detect. But for me, it's like 1, 2, and we have like 3 here. Fundamental mode, BO mode, and pitch mode is here, which is a good succeed, and we have more space below the SQL, which gives us more freedom to our measurement. Here is I draw the SQL over thermal noise ratio based on frequency, which is basically this part, to make it easier for me to do a study over other geometry of the microresonator, and I define Rmax, FAL, Fmax, and FH like this. So here also you can see how much is the difference between my design and the previous design. So here I did a study, so from now we are going to keep the thickness constant because we found it based on genetic algorithm. We know it's the best thickness. We shouldn't touch the thickness anymore, means this one, because if we touch it, we are gonna lose our reflection. But we can start play with like length of cantilever, R, and other parameter to find, based on changing this parameter, which one give us the better answer and which one help us to have better microresonator in overall. Because when I change the thickness, it means that the previous design of the length is not good for our design now. So if you do a study over the length, here you can see this way is frequency, this way is the length of microresonator. So you can see by increase the length of microresonator, the mode are decreasing, which what we want. And the Rmax, here is Rmax, which you have to see this graph is increasing, which what we want from 103 to 4.6. And also Fmax, we want it to be decreased, which beautifully decreased by increase the length. And you can see here FAL and BWE, which increase the BWE we have and decrease the FAL by increasing the L. I did the same study for width and also for size of the mirror pad, and I found that okay, if I decrease the width, I'm gonna get a better answer, and if I increase the R, it will give me the better answer. But here it's not gonna go like forever give me the better answer. Like up to L22 micrometer was the best result. After that it start to act vice versa. And also I found that the R, the dependency of Rmax, Fmax, and FL and PWD to the mirror pad radius is not monotonic due to different shifts in the frequency of the fundamental pitch and force mode. Also here you can see if we shift the place of the laser, means don't hit the laser exactly at the middle of the mirror, just shift it up and down. What's gonna happen is it doesn't affect on resonant frequency, but it affects the sharpness of the frequency, which you can see by increasing the L, but the Y, it gets sharper, which means it give me more space below the SQL, which was really good. And I also increased it as much as found that, okay, when it's the boundary, and I found that, okay, 5.75 is the best. If you go over 5.75, it starts to act exactly vice versa. So now let's back to your question. You asked me why we have a lot. So all this study happened for the previous one as well. So they make most of it to compare it. And also because these mirrors are very, very fragile and they might break during, transfer from the place we are making them. We even sometimes make some of them exactly same in one pack to make sure that, okay, we still have one to test here, which will happen to us that some of them came here and said, oh, it's break. But one is good, so we are good to test. So you can see that, like, for example, they have like different R changes or different So in summary, I have designed a new microresonator using the microgenetic algorithm and the finite element method, and study the effect of changing the geometry of the microresonator on the substandard quantum limit. The proposed microresonator outperformed the previous design in the subsquare regime, demonstrating lower thermal noise on the square, a broader subsquare regime, and the subsquare regime at a lower frequency. Thank you so much.
We're going to talk, question from Ryan.
Who actually makes mirrors? Is it LSU?
No, it's one of Dr. Corbett's former students. His name is Dr. Cole. I'm not